Okay, so what I want to look at today is the kind of stuff that I want to kind of pick up where we left off yesterday. Where we're going to look at functions, and we want to be able to. Ultimately, our goal is we want to be able to come up with sketches of the functions, right? And that's at this level, the sketches are going to be pretty rudimentary. We're doing the same thing in my calculus class, and the sketches get a little more detailed in my calculus class because we add more information about some parts of the function that we can't really do much with today. But in calculus we can. But we can kind of get the process started in Algebra 2. So if we take, for example, we looked at some examples of functions yesterday, and I'll just pull some of these up here. So, like we looked at stuff like these, right? If we graph a power function that has an odd power of x, so x cubed or x or x to the fifth, etc., they all have pretty much the same look, right? They all have what kind of symmetry would we say that was? Rotational. They have rotational symmetry. We called it's odd symmetry. And we name it odd symmetry because they're odd powers of x that give us this symmetry. And it's the rotational symmetry about what point? Where do I put the tack when I spin these functions? Yeah, the origin, right? So we'd say they have rotational symmetry about the origin, because that's the point where they're rotating. It's called the center of the rotation, right? And all we have to do is just push any one of these things around 180 degrees, half a turn, and they'll line up with themselves, right? Okay, so that's one kind of function we looked at. If we compare those to, what would be an example of an even function? X squared, sure. Let's take something like x squared. Okay, and I can zoom in a little bit. So there's x squared. I could do x to the fourth, x to the sixth, anything like that, right? Even functions, we name them because they're even powers of x have what kind of symmetry? It's different. What is it? What's the orange function has what kind of symmetry? Not rotational. Folding symmetry, good, or bilateral, or reflective symmetry, whatever you want to call it. Line symmetry is probably what we call it mostly in math. About what line? Fold them over, what is it, Joe? Y-axis, there you go, good, the y-axis. And we kind of talked about what these functions do as we get higher powers of x. I talked about music with you guys a little bit, right? Didn't we talk about? So if we get really big powers of x, they start to square off, right? But they still have that symmetry, don't they? Okay, what I want to look at today is we're going to limit this just a little bit. I want to go back to the end behavior stuff that we talked about yesterday, and let's take a different approach to finding the end behavior. We looked at a graphical approach. We relied on Desmos yesterday. So with this one right here, we could fill in. One second. Okay, so we said things like this. As x approaches positive infinity, f of x approaches, and you filled in the blanks. As x approaches positive infinity, which direction are we looking? Okay, to the right, aren't we? So that's if the ant's walking on the function. As he walks to the right, what's he do vertically? Goes up, right? So it's going like that. So we end up with the answer is f of x, or y, approaches positive infinity. And we see that from the graph. Okay? As x approaches negative infinity, f of x approaches what? Negative. Yeah, it's going down, right? And we even started to tweak the functions just a little bit at the end. We didn't get through everything, but we got enough. What if I do something like, if I'm going to multiply this function by a negative number? Let's just make it -1. Go back to our talk about transformations in Module 1. What happens if we multiply a whole function by a negative number? What's it do? What's it do? It makes it, reflects it over what line? the x-axis. Yeah, it reflects the whole thing over the x-axis, right? And that we can see that. It's no big deal. I mean, we saw that before. It just does something like that, right? It just reflected it over the x-axis, and so that changes the end behavior, doesn't it? Right? Now we'd have to go back and tweak this last statement a little bit. And we have to change that from a plus to a minus. Right? Because now as we go right, we go down. As we go left, we go up. Right? Agreed? Okay, but let's look at this a different way. Let's try to do this without the graph. All right? This is one of the things that makes you really good at math. And this goes all the way on through the highest math you can do. To get really good at math, it's important to be able to kind of marry the graphical stuff with the algebra stuff. And what I'd like you to be able to do by the end of the year is have a pretty good sense of, even if we're not graphing something, in the back of your mind, to kind of think, okay, if I did graph that, what would happen? You know, what might the graph look like? To be able to sort of interchange between thinking in those two ways. So let's take something like f of x equals negative x cubed, and let's try to come up with the end behavior using a little different approach. So we're going to fill in these blanks. Can't remember if we started talking about this, but I know we didn't finish if we did. So how many factors are there here? How many things are being multiplied in our function? What do you think? How many? One. I can see why people would say one. What would that be? Negative x. Okay, negative x. Now, if I changed this in one way, now it would be 1, right? Okay, but the way I had it, it's actually not. If we follow order of operations, let's think about order of operations for a second here. If I'm just simplifying something, what's the order in which I have to do the operations? Well, I have to do stuff in parentheses first. Okay, well, I don't really have any parentheses. But what comes next? Exponents. Exponents come before multiplication, right? And so technically, the x cubed comes before I multiply by the coefficient -1, right? So now, how many things are being multiplied there? You see it's, how many? Maria, you think you're going to say something? No? What do you think? Joe? How'd you get 3? Oh, okay, I see. Well, let's just assume this factor is one thing. Okay, so there's 2, aren't there? There's going to be the -1. We don't write the 1, but there's a -1 out front times the x cubed, right? And it's always going to be that way when we're trying to figure out how many factors are being multiplied together in a function. There's always going to be, once we get it into factor form, there's always going to be the coefficient times the individual factors. So what number is being multiplied by everything? Well, in this case, it's -1. What if it's a 1? Well, we don't even have to really count it then, do we? Right? But if there's any number out front, that could have been a -1, it could have been a +7, it could have been a negative pi, it could have been anything. There's some number out front, that's a constant factor, right? So what would happen then, because we've got these 2 factors, what's going to happen if we try to plug in a positive infinity? Okay, that's a weird concept. Technically, you can't do that. Infinity is not a number. But we can kind of get an idea what's going to happen. I would get -1 times positive infinity cubed. All right, well, what is that going to give me? If I have a number that's approaching infinity and I cube it, how big is that number going to be? Infinite, right? It's even going to be bigger than the number that I plugged into it, right? If I plug in like 1 billion and I cube that, I'm going to get an enormous number. Way, that's 1 billion squared times bigger than 1 billion, right? So it's going to get even bigger faster. So we know, the point is, we know that the outcome of this for sure is going to be infinite, right? We know it's going to be huge. It's going to be infinite. But what we don't know yet is what's the sign going to be, right? It's easy to find out though, because if we put in really big numbers, whether they're positive or negative, they still follow the same sign rules as any other number. They're just numbers, right? So we don't even really need to put that in there. We already know that the answer is going to be infinite. All we care about is what's the overall sign going to be. Well, if I put in a positive number, what's going to be the sign of the constant term? Always. What's the sign of the negative out front? The -1. Duh. Negative, right? I mean, it's not even, there's nothing you have to really think about there. That number is constant. It's never going to change, and it's negative. Okay, but what about this one? Now we've got this x cubed, right? What's going to be the sign of that number? That's the one we maybe have to think about just a little bit. Well, a positive number cubed is what? Positive. A positive number to any power is positive, isn't it? Does that make sense? Right? If I take a positive number and multiply it by itself as many times as I want to, it's never going to turn negative. It's always positive, right? So I get a negative times a positive, right? What's the overall sign then? If I multiply a negative number times a positive number, I get what? I get negative. And so negative is the sign that goes out front. Okay? That's a different way. We didn't even use a graph, right? But now we know what the end behavior is at the right end. How about the left? So as x approaches negative infinity, f of x approaches what? Okay, so let's do the same process again. There's two factors. We just need to know the signs of those. So if I'm plugging in a negative number, we know it's infinite, so I know the outcome is infinite, right? Just got to know the sign. You understand how we get that part, right? Does that make sense? If I plug in a huge number into this, I know I'm going to get an infinite result. As x approaches infinity, well, y has to, right? But what's the sign going to be? If I plug a negative number into this function, what's the sign of the first factor? Angelica, what's going to be the sign of that factor? I've got a -1 times an x cubed, right? The first one is just going to be the constant that's out front, so it's never going to change. What's the sign of -1? So negative, right? And we don't even care how big it is, we just know it's negative. How about the other one though? If I take a negative number and I cube it, Riley, what's going to be the outcome? A negative number to an odd power would be what? Negative, exactly. Because that's we talked about that a little bit yesterday. We always know that a negative number to an odd power is, no matter what the odd power is, it could be 101, it could be 1,000,001. It doesn't make any difference. If it's an odd power, it's negative. A negative number to an even power is positive though, right? Always positive. So in this case, that's odd, and so we get a negative result. So we have two factors. One of them is negative and the other one's also negative. So what's the overall sign going to be? Positive. Okay, so it's positive infinity, right? Okay, you try one. I want to see that we can do this before we move on. So this is important. So I'm going to give you a function. Okay, fill in those blanks. having trouble, remember, think about this in terms of the signs of the two factors. There's only two factors, right? So everybody, if you're going to do work on this, and I think some people were able to, I mean, eventually you can just probably look at this and see what the answer is pretty easily, but we're not probably there yet in most cases, and that's understandable. What we're going to do is we're going to have to think of this as a product of signs. What's the size going to be? I mean, what is this? We know it's going to be infinite, right? Everybody agrees? So we know for sure we can already fill that information in. It's just a question of what's going to go there and what's going to go there, right? What are the signs going to be? Okay. So yeah, let's look at the first one. We got two factors, right? The two factors are the -4 and the x to the 6th. Agreed? Okay. All we need to know is what's going to be the overall sign. So if I'm plugging in a positive infinity, what's going to be the sign of the first factor? Well, hold on. The first one's negative. The first one is just -4, right? I'm multiplying -4. The -4 is never going to change. That is my function, right? That's why we call it a constant factor. So I know, what's the sign of -4? Yeah, it's negative, isn't it? So I know that that's going to be negative, and if I do the same thing down here for negative infinity, that's negative for sure, right? That one's a given just because of that's a negative sign, right? So it tells me the coefficient is negative, right? That one's done, but this is the one I got to think about, right? So if I'm plugging in a positive number to the 6th power, Hannah, what's the sign going to be?
Negative.
Positive number to the 6th power. Yeah, positive number to any power is going to be positive, isn't it? Okay. What's a positive number, Emma, to our negative number to the 6th power? So that's even, right? So a negative number to an even power would be what?
Negative. Positive.
Positive, right? Maybe that's. I don't know. I'm not sure people are getting that part. I want to show you something. If I take a negative number, let's take something like -3 cubed. Let's just look at a couple examples. -3 cubed is going to be -3 times -3 times -3, right? If I multiply a negative times a negative, I get what? Positive. So pairs of negative numbers are going to give me a positive result, right? -3 times -3 is going to give me a positive 9 times a -3, and now a positive times a negative is what? Is what? Negative. So I'm going to get -27, right? Let's do something like -2 to the 4th. That's going to be -2 times -2 times -2 times -2. Well, look what I can do. I can kind of break this up into pairs, right? I know that when I multiply those two together, I'm going to get a positive. And when I multiply those two together, I'm going to get a positive, right? And so I end up with positive times positive is positive, right? Okay, but what if I do -2 to the 7th? Okay, so that's going to be -2 times -2 times -2. Okay, I can break these up into pairs. That outcome is going to be positive, right? That outcome is going to be positive. That outcome is going to be positive, so I'm going to get a positive times a positive times a positive. But I got one left over. It was odd. This one doesn't have a partner, right? Whenever I multiply an odd number of things together, and I pair them up, there's going to be one left over, right? So that's going to make it negative. So what's the overall sign have to be? Negative. Yeah, I'm going to get positive from all this stuff times that additional negative makes it negative, right? Now, if this had been to the 6th power instead, well, that would have worked out differently. Then I wouldn't have had that extra leftover guy, and it would have ended up being positive, right? So for that reason, we always can say a negative number to an even power will always work out, so I can pair up each of the negative factors, right? So they'll cancel each other. But if it's odd, I'm going to have that one oddball left over at the end that's going to make the overall sign negative, right? Okay, so going back up to the problem then, I know here that if I'm plugging a negative number into x to the 6th, I got an even number of negatives multiplied together, so it has to be positive, right? So what's the outcome of the top one? Negative times positive is what? Negative. Negative 4, x to the 6th ends up being positive, and so I get a negative infinity. How about the bottom case? If I plug in negative infinity, I got negative times positive is also negative. Right? See how that works?
I got two negatives.
How did this become negative though?
I just thought of the graph.
Oh, don't think of the graph. Yeah, don't think of the graph. The graph, if you're given a graph, that's one thing. But otherwise, just do it this way. Okay, and here's the reason why. Let's look at a different function. This is pretty cool. So let's look at a polynomial now. And you're going to see something really important coming out of this. Okay, so here's what the function is this time. We've got, I'll write this down so we can always look at it up here. So we've got, I'll write it up here. F of x equals 0.000001 x to the 4th plus 0.001 x cubed plus 0.1 x squared plus x. Okay, this is a polynomial, right? It's a collection of terms, and each term has some real number times a whole number power of x, right? Okay. What does it do if I multiply a function by a number? Like if I take, for example, if I take the function, just for a second here, if I take the function x cubed and I multiply that function by 2, what's it going to do? Think back to module 1. That's like a, right? What if a was bigger than 1? What did it do to the function? Oh, what did it do? Here, I'll just put, there's x cubed, and here's going to be, let's make it x squared. It's a little easier to see. So there's x squared. Here's 2x squared. Oh, whoops. What did it do? It stretched it vertically, didn't it? Right? So what if I make another function that's like 0.1 x squared? Oh, darn it. Oh, caps lock. What did it do now? What'd that do? Maybe let me zoom out a little bit. What did it do? What's the purple one do? It didn't stretch it, it compressed it vertically, right? Everybody see that? So when I do something like this, if I multiply a function by a really, really small number out front like that, it's going to compress it a whole bunch, isn't it? Right? It's going to make that term less powerful in a way, isn't it? Right? So let's go back to this other function, and let's explore this a little bit. So there's the function. Now the question is, I want to know which part of this function dominates the behavior, right? Which is most important? Well, think about these terms one at a time. This term over here, y equals x. If I just were to graph y equals x by itself, what would that look like? It'd look like a line, wouldn't it? With a slope of what? Slope of 1, y-intercept of 0. Okay, so let's try that. Let's graph another function right along with this one. What if I graph the function y equals x? Oh, it lines up perfectly, almost, right? It barely deviates from it up there just a little bit, but it looks almost exactly like the function y equals x, doesn't it? Everybody agree? So can we just be done with this and name a winner? That's the term that wins. That's the term that it looks the most like. Everybody agree? Okay. All right. Well, I guess we're done. Let's go on. Let's go on here and see what happens. Uh-oh. Something happened. When I zoom out, something happened. It doesn't look like that at all. Doesn't look like that at all. Something weird happened. Now, okay, so it doesn't look linear anymore. What's it starting to look like now? It's starting to look like a parabola. Well, which of these terms up here would look like a parabola? Oh, the x squared, right? Okay, it's a pretty squashed down parabola because that's a pretty small coefficient, but it's starting to look like a parabola. So, okay, so we gotta make a little change. So the winner is not x. It looks like it's the x squared term. We done? All good? All right. Okay, we're good. All right. Well, let's move on a little bit here. Let's go out here. Oh my gosh, what's going on? What's going on? Oh, okay. Well, we gotta fix this. What's that look like? What's that look like?
That's the x cubed.
That's the x cubed. That has the end behavior, right? Now it looks like a cubic. It's going to go down on the left and up on the right. Okay, so it's the cubic, right? We can be done with this. Well, obviously you kind of you get what's going on. If I go out some more, we got time? Look what happens. So there's a really important moral to this. So if we keep going out, then eventually which term is going to win?
X to the fourth.
X to the fourth. And if we keep going out further, it starts to look kind of inconvenient because the x-axis is so scrunched. So I'm going to change the x-axis a little bit here. If we change the x-axis to be, how about if we go, okay, so if I really compress the x-axis or stretch out the x-axis a little bit, we can see this a little better. So if I keep zooming out, now it's starting to look more and more like a normal x to the fourth function. And I'll do that same trick one more time. So I'm gonna stretch out the x-axis one more time. And then look what happens. Okay, these are big values, right? Now let's look at the scale of this graph. If you look at the scale of this graph, I mean, this is like, that's negative 10,000, that's positive 10,000. Look at the y values. I've got 10 to the 8th, so that's, what, 100 million? There's, what do we got, 1.5, so there's 200 million. We're getting big, big numbers. But there's no end to how big numbers get, right? These seem like big numbers, but on certain scales, they would be tiny. But even on this scale, that looks a lot like one of the graphs we had yesterday, doesn't it? Doesn't that look just like the quartic function, the x to the fourth function? Mm-hmm. At this scale, can you even see this other junk? You can't even, that line and the parabola and the cubic function, you can't even see them. They're gone completely, aren't they? Right? And if I go out further, this thing would look exactly like a quartic function if I keep going out now further and further, right? So what's the moral of the story then? I mean, this may not seem like a big deal, but this is huge. This tells us something really important about the way functions behave. It takes the shape of the largest term. Yeah, if we look at really large values of x, which is really just end behavior, isn't it? As we go out infinitely far to the left or the right, only one term ended up mattering. The only term that mattered was the term with the biggest power of x, right? And we call that the leading term, right? So that makes life pretty easy. If we want to know what the end behavior is of a function, just look at the end behavior of the leading term and forget about the rest of it, right? So let's try an example. So if we do something like this. How about if I give you the function? I'll make it really a complicated polynomial. If we've got f of x equals negative x to the sixth minus pi over 3 x to the fourth plus the square root of 97 over 2 x cubed minus 0.0123x plus square root of 2. Complicated polynomial. If I want to know the end behavior, though, what part do I consider? That's it. All I have to think about, if I want the end behavior, is just this part right, whoops, just this part here. Right? That's it. So when I want to answer the question, as x approaches positive infinity, f of x approaches what? Just go there. How many factors are there? Not one. Two. I've got the negative times the x to the sixth, right? So all I got to do is figure out what the signs of those are going to be. So f of positive infinity, if I plug positive infinity in for x, what are the signs going to be? First one is negative. Second one is positive. Positive to an even is positive, and so the overall sign is? Okay? Make sense? Okay, if I want to do as x approaches negative infinity, f of x approaches what? Same deal. F of negative infinity, what's first sign going to be? Negative. A negative number to an even power is, Emma, what's that going to be? Negative number to an even power? Positive, there we go. So we get negative overall. Negative times positive is negative. So it's negative infinity, right? Okay. We could even go one step beyond that. And this is going to look like it's something harder, but it's actually easier. So what if I gave you something like this? F of x equals, how about negative 2x squared times x plus 3 times x minus 4. And I want to know the end behavior. Okay, this is not written in standard form. This is a polynomial in factored form, right? And it's going to be really useful to us in sketching the polynomial. So it's actually to our big advantage to have it in factored form. But when we want to do the end behavior, we've got to think about this just a little bit. If I were to multiply all this out, what would happen? A lot would happen. But we can kind of see how that's going to go. Let's take, for example, what if I were to multiply those two together? What's going to happen? If I distribute the x squared to both parts, then I'm going to get a negative 2 times, what's that going to give me? X squared times x is, no, x squared, if I multiply like bases, I add the exponents, right? X cubed. X to the 2 times x to the 1 would be x cubed plus, who cares? Yeah, watch closely. Hang on. You really got to focus on that. I know there's a lot of stuff, but you're going to have to do all this. On the next test, you have to do this on paper and pencil. We're going to have a paper and pencil test where you got to be able to do all this. Okay, so I don't care what the other stuff is because ultimately all I want is the leading term, right? So if I'm going to multiply that then by x minus 4, I don't care about all this other garbage. All I care about is what happens when I distribute the x cubed, right? When I distribute the x cubed, what's that first term going to be? X cubed times x to the 1 is x to the 4th. Plus a bunch of other garbage I don't care about, right? Now I've still got this minus 2 out front. When I distribute that all the way through, don't I end up just getting negative 2 x to the 4th plus, who cares, right? Doesn't make a difference. That's my leading term. Agreed? So, sure, you can put that in the board, definitely. So the point is, really, all we had to do was multiply that times the constant out front, and we got it, right? Everybody agree? So when I want to determine what the end behavior of that function is, I just look at that, and that's it. What are my two factors?
Who cares?
Who cares? No, that we do care about. I got a -2, right, times x to the fourth. And so when I plug in like positive infinity and negative infinity, I'm just going to need the signs of those two factors, right? Make sense?
Are you gonna put,
Okay, so yeah, so your homework. We're about done, right? 25? Okay, well, we didn't quite get where I wanted to. So, yeah, the homework. For now, everybody pick up one of these. We're not quite to the point where you can do this yet. I'm going to plug in one more thing tomorrow, and then you can work all day tomorrow on this. I'm trying to get the Moodle stuff done for this, but it's really, really complicated. I don't know if I'm going to be able to do it in the next couple of days. For sure, I think I'll have it done by the time we do a test. I can give you a practice test with Moodle problems, but for now, we're going to have to do paper and pencil.
I